each other. So I have to keep that in mind down here. If x is gone, then y to the fourth and z to the fourth, it must be the same magnitude, they must equal 1/2. So then I just take the fourth roots. So then if you do that, and you take these, and you plug them into f, we're going to get 0 plus the square root of a half plus the square root of half again. So f is going to be 2 times the square root of 1/2, so it's going to be the square root of 2. And then the last possibility is none of these are 0. Well, in that case, x, y, and z are equal to plus or minus the fourth root of 1/3. So I raise these to a fourth power, I must get 1/3. So that'll satisfy the constraints. So then, if I take these and plug them into f, I'm going to get square root of 1/3 plus square root of 1/3 plus square root of 1/3. So I'm going to get f will be 3 square root of 1/3. So that's the square root of 3. So this is the min. This is the max. That turned out to be the one in the middle. That's not anything. So all of this comes from a conclusion that, based on what was done here, the only possibilities are 0, 1, or 2 of these guys are 0, and whatever's left are the same in absolute value. So then I just worked with this from that point on. I didn't bother to find a value of lambda. So that would be a pain. This is something actually that seems to happen a lot with these problems, is because of often you get constraints of this form, or maybe it's x squared plus y squared, something like that, and you're in a situation where you're concluding that like two of the variables have to be plus or minus each other. So solutions like that tend to be fairly common. Like, or you include like x must be equal to plus or minus z, and when you plug into the constraint, you figure out what they are. So algebraically, that's something that's likely to happen. So, yes?
So could you have, say, for the second possibility, could you have like y equals the plus minus a fourth root of 1/4 and z equals plus minus a fourth root of 3/4?
No. These are the only possibilities. Now, if this problem was made with 4 variables, and everything else worked out the same, then yeah, you have more possibilities like that. But here we just have 0, 1, or 2 of these variables equal to 0, so at least one of them must be non-zero. And then we see what's going on. Yeah, so if you had any number of variables, all the solutions would be, f would turn out to be the square root of 1, square root of 2, square root of 3, all the way up. Okay, so I'm just seeing under what are the possibilities for this equation being satisfied, and this is just because we have a power of x in each one, and say, oh, x could be 0, and then so when I rule out x being 0, then I go ahead and simplify this, and that's where this possibility came up. Yeah. So that's something, actually, this is a good warning sign for all these problems. Because it's tempting to look at something like this and say, oh, x equals 0. Consider the case, what if x is not 0? Make sure you cover all the bases, or you'll miss a solution. Yeah. All right. Now, imagine one thorny issue when it comes to integrals is setup, and also change of variables. Okay, let's find a juicy one here. There's a section of review exercises at the end of a chapter. This is number 25. We're integrating, and the solid is described by this paraboloid and this plane. Okay, so what that's looking like. Okay, so right here, that's the plane x equals 0, so for a paraboloid, sometimes it's easy to visualize it by setting one of the variables involved equal to 0. So for instance, if we said z equals 0, then we see what this looks like in the xy plane. So x is 1 minus y squared, so you're looking kind of like this. Whereas if we set y equal to 0, then x is equal to 1 minus z squared. So we get something like this. All right. So it's this portion right here. So the fingertip, if you will, of a steadily growing in width finger, going all the way back. Is,
like a cheese finger.
Yeah, okay, we'll go with that, I guess. And that's the solid that we're integrating over. Now, if you set when x is equal to 0, so a projection of a solid onto this plane, we have y squared plus z squared is equal to 1. So that suggests using polar coordinates for y and z, and then you're leaving x as it is. So what we could do is polar in y and z, we could set y is equal to r cosine theta, z is r sine theta, and then this is the unit disk right here. So we have r going from 0 to 1. That just comes from this. And then theta goes from 0 to 2 pi. That's because we're going all the way around. There are no restrictions on this paraboloid. Now, on the other hand, if we had said that this was also bounded by the plane z equals 0, then that would restrict theta. So, for instance, it would be like theta going from 0 to pi in that case. So the variables we now have are r, theta, and x. So we need to write our triple integral in terms of these variables and figure out what the limits are. Okay. So now x depends on both y and z. So x runs from 0 to 1 minus y squared minus z squared.